Hi everyone. I'll be talking about our survey on automated reinforcement learning, or AutoRL for short. AutoRL involves automating various components of the RL pipeline, such as the hyperparameters and the algorithm itself. We formulate this as a bi-level optimization problem where, as we see on the slide, we have an inner loop where the usual RL optimization of maximizing rewards in an environment takes place, and we have an outer loop where the components of the pipeline are optimized. So why do we need AutoRL? Reinforcement learning is highly sensitive to design choices and expensive to tune. Various papers have highlighted how even tiny implementation details can lead to dramatic changes in the performances of RL agents. AutoML has had very good results in other parts of machine learning, and applying it to RL has shown signs that it can be far more efficient and better performing than trying to tune by hand. However, AutoRL encompasses more than just the application of AutoML to RL, due to unique challenges of its own, such as having to deal with non-stationary loss landscapes. Existing approaches like meta-RL, curriculum learning, and more can be categorized as AutoRL approaches, and AutoRL has been gaining momentum as the potential is becoming clearer. On this slide, we see a visualization of what needs to be automated for the RL pipeline. We group these tunables further into the learner tunables and the actor tunables. Under the learner tunables, we tune the hyperparameters, the batch size B, for example, or the discount factor gamma, and the algorithm, for example, learning the best parameterization of the loss function to use. Under the actor tunables, we tune the network architecture used by the RL agent or even the environment itself. On this slide, we see the categorization of AutoRL approaches in our work. We survey relevant literature for each of these and describe the properties of each class. For example, this property tells us if the approach tunes online in a single run or if it requires multiple tuning runs. And this one tells us if the kind of tuning performed is dynamic or static. We also describe what component of the pipeline is usually automated in each class. In the survey, we also pose open problems for each class of approaches. I'll now delve into more details for each of these categories of AutoRL. We begin with the basic approaches of grid and random search. They are the most commonly used methods as they are easy to implement. They are also good for visualizing the loss landscape. However, they do not use any information obtained during the optimization and as such are inefficient and do not scale well. On the right, we see a visualization of grid and random searches at various points during the optimization. The objective function with respect to a single hyperparameter is visualized on the sides here, and we can see the dynamic loss landscape as the objective changes during the optimization. We also notice that grid search samples points uniformly for important and unimportant hyperparameters. As such, it reduces efficiency. Neither of these approaches are dynamic, and thus they can neither capture nor optimize for the dynamic loss landscape. We move on to Bayesian optimization, or BO. BO builds a model of the response surface using information obtained during HPO. This helps us be more efficient by querying points that are expected to perform better. On the right, we see a visualization of this process. An acquisition function combines the model with uncertainty information, which allows us to balance exploration and exploitation. Using the acquisition function, we sample the next point to evaluate, which leads to further improving the model, and this continues iteratively. AlphaGo, the prominent paper from DeepMind, employed BO to improve its win rate from 50 to 65% in self-play. In order to speed up BO even further, there are various multi-fidelity approaches. For example, Bob has been used for tuning the architecture and hyperparameters for learning to design RNA. BO for iterative learning is an approach that uses knowledge of the learning curve to model it as a sigmoid and then sample better points using this model and to speed up the training. A drawback of BO-based approaches is that there aren't many approaches yet that perform dynamic tuning. Evolutionary approaches maintain populations of optimizees and mutate their members at certain time steps. A popular example is population-based training, or PBT. We see PBT visualized on the right. The hyperparameters are shown as the heads, and weights of a neural network are shown as the bodies of population members. The performance bars over each member show how the member is performing. Every few time steps, the top members are chosen to replace poorly performing members in an exploit step, and their hyperparameters are perturbed slightly to explore around well-performing regions of the hyperparameter space. This allows to also have dynamic schedules of hyperparameters, and PBT-like approaches are popular for this dynamism in spite of being resource intensive. As a result, a lot of follow-up approaches exist, including PB2, which augments PBT with the time-varying Gaussian process model to improve efficiency. Metagradient-based AutoRL approaches tune hyperparameters online in a single run using gradients of an outer objective with respect to the hyperparameters. They optimize the usual RL objectives in an inner loop, keeping the hyperparameters fixed. These approaches are efficient, but the drawback is that they can only be applied if the outer objective is differentiable with respect to the hyperparameters. The original metagradient RL paper considered the gradients of the outer objective with respect to the discount factor gamma and the bootstrapping hyperparameter lambda, and improved over the state-of-the-art actor-critic agent Impala. RL darts is another metagradient approach applying the neural architecture search method darts to the RL setting. We also see a visualization of the MAML approach, which optimizes for common initialization parameters theta by taking metagradients with respect to theta. Blackbox online tuning is another set of methods that tunes hyperparameters online, but as the name suggests, they do not need differentiable outer objectives. Examples of this kind of approach are Agent 57, which achieves state-of-the-art results on the Atari benchmark using multi-arm bandits to select from several exploration policies. The Hoof paper uses random search in a hyperparameter space that includes the discount factor gamma and the bootstrapping hyperparameter lambda. It calculates the objective using returns estimated with policy gradients and uses these to select better performing hyperparameters dynamically. These approaches are more flexible, but they can be inefficient. Learning RL algorithms includes many popular meta-RL approaches. Here we have two broad classes of algorithms. One is the learning-to-learn formulation, which includes approaches such as RL squared, which uses an RNN with the past history as input to identify among the set of interrelated tasks and solve them. The other class is meta-learning a loss function. The loss function could be represented by a neural network as was done in evolved policy gradient. It could also be represented as a symbolic expression, for example, a directed acyclic graph as was done in evolving reinforcement learning algorithms to find the best parameterization of the loss function. We see this depicted here. Finally, we move on to environment design, which brings a whole range of existing RL approaches under a common umbrella. We consider the environment to be a partially observable Markov decision process with the usual components. Any of these components might be optimized to try and improve the final performance of an RL agent, for example, the reward function R or the action space A. On this slide, we see some example environment design approaches. Reward shaping approaches are very well-known methods that optimize the reward function. AutoRL, by evolving rewards, use evolutionary search to optimize a parametric multi-objective intrinsic reward function to improve performance on 4 Mujako continuous control tasks for 2 RL algorithms. Coming to optimizing the observation space, DRAC is an approach that achieves state-of-the-art performance on the ProcGen benchmark by using bandits to optimize image transformations to apply to the observation space. It also performs well on DeepMind control tasks. Curriculum learning approaches such as POET and PAIRED can be seen as modifying the initial state distribution and the state or observation spaces to present easier problems initially to speed up learning. These approaches are unsupervised. Finally, a supervised approach that optimizes multiple environment components at once is learning synthetic environments that represents the dynamics and reward functions as neural networks and optimizes these in an outer loop. Thank you for watching. For more on our work, please visit our poster. We look forward to greeting you at AutoML Conf.